attack still works even after previous fixes. In the next few minutes, you'll see how attackers use a legitimate IDE feature to bypass earlier mitigations and regain code execution. Let's break it down. Just when we started putting guardrails, the attacker finds a way to take the wheels off. This case study builds on the previous RCE but goes a step further, showing how an attacker can remove even more constraints using the multi-root workspace feature in VS Code. It's like a masterclass in creative exploitation. Multi-root workspace, it allows developers to open multiple folders in one workspace or project in VS Code. Now here comes the twist. When you do that, the configuration isn't .vscodesettings.json anymore, but in a separate .code workspace file, which can live anywhere. This flexibility is great for legit use and for attackers. This slide's attack flow likely shows expand the workspace to a targeted folder. The AI is instructed to edit the .code workspace file or create one to add an additional folder path. Any path on the file system that contains a writable executable file. Why? This tricks VS Code into treating that external folder as part of the workspace. Critically, it gets around the typical safety measure. Normally, if an AI, it tried to edit files outside the workspace, many tools would require user approval. But by redefining the workspace to include that folder, suddenly those files are inside and fair game. The researcher crucially notes here that this bypasses the common human-in-the-loop restriction for out-of-space edits. Now, malicious code injection. Now that the new folder, may be some system directory or just another location on disk, is part of the workspace, the AI can edit an executable file there and inject malicious code. This is similar to step 1 in case 2 that we discussed earlier, except now that the file didn't have to be originally in the project. It could be anywhere the attacker knows about. For example, maybe there's a known binary in a standard location that's writable by the user. Configuration override. The AI then edits the same .code workspace file to set a configuration like the PHP validate executable path again to point to that newly edited malicious executable. Trigger execution. Finally, as before, it creates or opens a file like a .php file to trigger the IDE to execute the malicious code via that config. Boom! Code execution achieved. The genius of this method is it removes a precondition. In case 2, we needed an executable in the workspace to start with. If a project was completely empty of any executable files, maybe the original attack would have to first put one there, which might raise flags. But with multi-root, you can pull in any folder that has an executable, such as maybe the system's TMP or some user-level binary directory where there's usually something to abuse. It removes the executable file in workspace precondition, as the researcher notes. From a defensive standpoint, this is a nightmare because it means any file on disk that's writable by the user could potentially be leveraged. The scope of what the AI can tamper with just exploded beyond the initial project folder. It's showing the endless features problem. Fix one, another appears. The multi-root feature itself isn't a bug, it's a core VS Code feature working as intended. But combined with an AI agent, it becomes a tool for exploitation. This slide probably emphasizes how this demonstrates the real risk of IDE disaster. You patch one path, say VS Code settings JSON case, and another opens code workspace case. It implies that unless you systematically secure all such features, attackers will keep finding new ways. This is why we call it a vulnerability class. Legally and policy-wise, this case underlines the concept of systemic failure. For regulators or industry groups, it suggests that piecemeal fixes aren't enough. There may need to be guidelines that cover categories of features. For For example, an advisory could say, review all configuration-driven executables in your IDE and ensure AI cannot tamper with them without user consent. It shows the importance of responsible disclosure and patch timelines. The researcher held back the exact exploit prompts in these cases, did not publish them, precisely because vendors needed time to patch, but even after 90 days, some hadn't patched. This raises an issue. In a systemic issue like this, do we need a more coordinated response? Should, say, the maintainers of VS Code and JetBrains coordinate fixes across all downstream projects? It's akin to a supply chain one like Log4Shell, which affected many apps. Often we see government agencies get involved in such widespread cases to facilitate info sharing and patching. If companies know these risks and fail to mitigate, they could be held accountable by regulators. For example, financial institutions have regulations to secure their software development process. An IDE compromise could fall under operational risk. Governments might push IDE vendors to harden their products, especially ones heavily used in critical sectors. Conversely, state-backed actors, cyber espionage, might exploit these kinds of vulnerabilities to infiltrate organizations. It's a bit of arms race now. We have to assume sophisticated attackers are reading this research too, and even this video, and maybe try to use these techniques. In summary, this slide shows an even more flexible attack, a testament to how many doors can open once an AI is inside an IDE. It underscores that we can't just whack-a-mole these vulnerabilities. We need a broad strategy. That's exactly where we turn next, understanding disaster as a class and how to systematically defend against it.